So in the L1 norm regularized least square problem, which is the loss function is simply two terms A of W plus lambda times R of W. In the previous part lecture, we saw that to minimize A of W, we can have an iterative algorithm where we replace this function by G of K, and the solution becomes a Land-Weber iteration, which we discussed in the previous part lecture. And this part lecture, so the G of K was simply some beta times some vector B minus W normal squared plus some constant term Vk. So in this part lecture, we will discuss what is known as soft threshold, and we'll have a loss function C of K, C of W, which is equal to some constant vector V minus W squared, L2 norm squared, plus lambda times L1 norm of W1. So this loss function C of W is a special case of our original loss function G of W, which was norm of Y minus phi times W squared plus lambda times L1 norm of W. So the loss function C of W is a special case of G of W by setting V equal to Y and phi as an identity matrix. So now we will see how can we minimize this loss function, and once we obtain a solution for this, we will combine the previous power lecture where we minimized a loss function G of K. We'll combine the two results to obtain the iterative soft thresholding algorithm. So we can see that C of W, can be written as, since there is no matrix phi, this would simply become sum or all I equal to 1 to n, where n is the dimension of the vector W and V, Vi minus Wi squared. We just expanded the definition of the L2 norm, where I denotes the ith component of vector V, plus lambda times absolute value of Wi. We just expanded the definition of the L1 norm. So we can simply write it as sum or all I equal to 1 to n Vi minus Wi is squared plus lambda times absolute value of Wi. So we can see that since each of the term doesn't the quadratic term, because of the absence of matrix phi, all the terms should be uncoupled, and that's why we can simply write it as C of W. Again, we'll just write it here again as Vi minus Wi squared plus lambda times absolute value of Wi, sum all I equal to 1 to n. And now, since each of the individual components of is decoupled, so minimizing this loss function C of W is same as minimizing the individual n different loss functions, where the loss function Si of W is equal to Vi minus Wi squared plus lambda times absolute value of Wi. Since the uncoupled terms means that we do not have in this, because of the absence of matrix phi, we will not have in this, if we expand this, we will not have any term like wi times wj, where I is not equal to j. So because of absence of any such term, we have decoupled functions, and minimizing this loss function c of w is same as minimizing individual scalar loss functions. So, and each of these function si is convex because this function is convex, and as well as this function. So we can write minimizing c of w is same as minimizing the individual loss functions si w for I equal to 1 to n. And now we will see how we can minimize this loss function si, which takes the scalar input. So we can just write it as wi to show it's dependent, or we can remove the subscript I from here. So we can just write it as s of wi to show that this is a scalar function. It takes a scalar input and returns a scalar as an output. So now we will minimize the function s of wi, which is equal to vi minus wi squared plus lambda times absolute value of wi. So this function s of wi is convex because this squared function is convex function, and so is the absolute value function wi. And we can minimize it by just setting its derivative with respect to w to 0. And the derivative or the gradient of the function swi is simply the gradient of this term plus the subgradient of this term. Because this is not differentiable, so we'll compute the subgradient. And now if you recall our lecture on the subgradient methods, then for any convex function f of x, a point x star is a minimizer of function f if the subdifferential set of f at x star contains a vector of 0. That is, one of the subgradient of this function is 0. So in simply we write x star is minimizer of f of x if the subdifferential set of f if the zero subgradient, that is a subgradient whose all components are 0, if 0 belongs to the subdifferential set of f at x star, where subdifferential set, as we recall, is a set of all the subgradients of function f at point x. And since this s of w is convex and non-differential non-differential function, so effectively the gradient of this plus the subgradient of this results into the subgradient of this function s. And the optimality condition, the minimizer of this function is given by the point that contains the minimizer of this function s of w is some point wi star such that the subdifferential set of s at w star contains 0. So we can compute the subgradient as d by dwi is simply the gradient of this term, which is equal to negative of twice of vi minus wi plus the subgradient of this term, which is simply lambda times sine of wi. where we define the sign of Wi as to be 1 for Wi greater than 0, any value between -1 and 1 for Wi equal to 0, and -1 for Wi less than 0. We had seen this in the subgradient lecture as well. So if we plot this absolute value function, then we see for Wi greater than 0, the subgradient is equal to the gradient, which is 1. For Wi less than 0, the subgradient is equal to the gradient, which is -1. And for Wi equal to 0, any subgradient, any value between -1 and 1 is a valid subgradient of the function absolute value of Wi at Wi equal to 0. So that's why we define sign of Wi as 1 for Wi greater than 0, or any value between -1 and 1 for Wi equal to 0, and -1 when Wi is less than 0. So the optimality condition states that the 0 should be contained in the subdifferential set at the optimal point. So we just set the subgradient of this to be 0 to obtain the solution for Wi as Vi is equal to Wi plus lambda over 2 times sine of Wi. So now we can solve for Wi over here to obtain that Wi equal to Vi minus lambda over 2 sine of Wi. Now because of this sine term, there are going to be 3 different cases. So we can write Wi is equal to Vi minus lambda over 2 when Wi is greater than 0. That is, when Wi is greater than 0, then the sign of Wi will become 1. So for this solution, Wi should be greater than 0. So this is a solution when Wi is greater than 0. The second condition is that when Wi is equal to 0. So in that case, we have Wi is equal to any value between -1 and 1, Vi minus lambda by 2 times any value between -1 and 1 when Wi equal to 0. And Wi is equal to Vi plus lambda by 2 when Wi is less than 0. So it is a bit confusing as to what we mean to do over here. We are writing the solution as W, but we are writing condition that Wi is greater than 0. So now it will become much clearer. So the first condition states that when Wi is greater than 0, the solution for Wi is Vi minus lambda by 2, which means that this term should also be greater than 0. So we obtain this condition roughly reflects Wi equal to Vi minus lambda by 2 when Vi is greater than lambda by 2. We also see that Wi is equal to 0 when Vi is less than or equal to lambda by 2 and is greater than or equal to negative of lambda by 2. We see that Wi is equal to Vi plus lambda by 2 when Wi is less than 0. So this term should be less than 0. So we obtain Wi equal to Vi plus lambda by 2 when Vi is less than negative of lambda by 2. So now we can write the solution more effectively as we have Wi equal to Vi minus lambda by 2 when Vi is greater than lambda by 2. We obtain that Wi is equal to 0 when Vi, absolute value of Vi, is less than or equal to lambda by 2. We obtain Wi equal to Vi plus lambda by 2 when Vi is less than negative of lambda by 2. So this is the solution for minimizing the loss function norm of V minus W squared plus lambda times L1 norm of W. And now, so this L1 norm. So now we can write this solution more complex. So this would be for every Wi. So for I equal to 1 to n. And now we define a function which we call as soft threshold function, which will denote as soft of two values x comma nu. So soft takes two arguments x and nu and is defined as soft of x comma nu is simply equal to x minus nu for nu greater than x, for x greater than nu. It is defined as 0 for mod x less than or equal to nu, and is defined as x plus nu for x less than negative of nu. We can also write this more compactly as it is sine of x times max of 0 comma absolute value of x minus nu. Where we had defined, here we will use a different, so we can write it here sine prime, where sine prime returns 0 for x equal to 0. So earlier we defined the sine function as having value anywhere between negative 1 and 1 for x equal to 0. But now we define a new function sine prime which is equal to 0 for x equal to 0. So this is the definition of the soft function. And now comparing with the earlier result that we had, that Wi equal to Vi minus lambda by 2 when Vi is greater than lambda by 2, equal to 0 when absolute value of Vi is less than lambda by 2, and Vi plus lambda by 2 when Vi is less than negative lambda by 2. So we can see that by comparing, so I'll just erase this to remove clutter. So we can see that Wi comparing this and this, we get Wi is equal to, so this function, by comparing this, we can write it as soft of Vi comma lambda by 2. So summarizing everything, we get the solution of this function C of W, which is equal to norm of V, where V is some vector, minus W L2 norm squared plus lambda times L1 norm of W. The solution, the minimizer, is given by vector W, which is equal to soft threshold function of V, where V is vector, comma lambda by 2. So this is the minimizer of this function C of W. And now, in the previous power lecture, we saw that that the first term, to minimize the first term of a loss function g of W, we constructed a function g of k, where we had a simple definition of function gk as g of k was equal to norm of beta times norm of some vector b, where v was defined in the previous lecture, minus W plus some constant term that was independent of W, and the original loss function g of W was equal to function g of W, because we replaced the original loss function E of W by G of W in the measuration maximization, plus lambda times norm of W1. So we'll now combine everything in the next power lecture to see how to see the solution of our original loss function, which was y minus phi times W square plus lambda times L1 norm of W. So in the next power lecture, we'll combine all the results to finally obtain the solution, the minimizer for this loss function, and that algorithm would be the iterative soft thresholding algorithm.